Okay, so we're starting with our sessions in here today. Mathieu Gerard's going to talk about his open source framework that he developed, so please enjoy.
Hi, good morning, everyone. Thank you for attending the presentation. Not easy to be on stage after Guy, but we're going to try to enjoy some interesting talk today, especially because not all the slides have a black background, and I've checked the minimum font is 28, so it should not be too bad for now. But so yeah, thank you for being here. And we're going to speak about the open source framework for indoor location. And as Guy also spoke about, so he said there are different maps. So we have maps 1.0, maps 2.0, 3.0 with the traffic, and let's see if we're getting into maps 4.0 with the indoor. So I'm Mathieu Gerard. I'm from France. That's where we have based our company Mapwize. So I have an engineering background. I did my PhD in systems and control. It's a bit between signal processing and robotics. And so today I've been founding Mapwize a few years ago with the idea of bringing maps to the inside of the building. So we really saw that there was some interesting things to do over there, and so that's why we created that. So it's based in France and visiting for the conference. So as I say, Mapwize, the objective is to bring the maps to the inside of the buildings. And so what we are creating is tools for building managers to digitalize their maps, and then the SDKs for developers to use them into their own mobile applications. And maps have been around for centuries. So that's one of the extremely old map that we can find from civilization, from 1300s. And so from the very beginning, people have been trying to represent the world they live in, and so also provide the tools in order to be able to find their way around in areas that they haven't been visiting before. And so 20 years ago, maps looked a bit more like that. So that's the map 2.0 that Guy was mentioning. So we had a lot more work that has been done in data acquisition, putting the roads out there, but it was still a paper version of the maps. And so you remember they were printed in different scales. You would have to open different maps if you wanted to get into more details. And it was quite hard to navigate on those maps and to know I need to go from point A to point B, how I'm going to do that. The eternal debate, are men better than women at navigating on the maps? But let's not get into that debate right now. So we would really have to put some effort in order to use them. By the way, so Lille is right in the middle. That's where the company is based. And so London is on the top left, Paris on the south, and Amsterdam on the top right for those who know a bit more those cities in Europe. And so, of course, if we look at maps today, we see that it's completely different. It's completely digital. You can zoom in and get an incredible level of detail just by simply scrolling the mouse or pinching your phone, and you can really get a lot more data in your pocket. And so it's also daily updated and so on. And if we come back to location, since the very beginning of time, people try to realize where am I on that map. And so, of course, if you're on Earth, you can use the visual clues that you see around you. What do I see? What buildings do I see? What road do I see? If you don't see, it's much more complicated. And so that's one of the sextants. It's really interesting to see how it's actually works, because we've all seen those things in museum. But basically, you need to measure the angle between the horizon and the sun at noon. So once per day, you will get a measurement of your latitude. So how far you are from the equator. The higher the sun goes in the sky, the furthest, the closer you are to the equator. So that would give you one measurement per day, and only if it was sunny, so you could know how high you are compared to the equator. If you need to get your longitude, you would need to get an extra tool, which is a clock that would measure the time that it is at the place you departed. And so at noon, you would know that it's a certain time where you are, and you would check what time it is at departure, and the difference in time would give you how much you've been traveling across the globe. So again, pretty complicated to get, requiring good time measurements, which was not easy at the time, and so you would get one measurement per day. So really, really interesting, and people have been doing it for centuries until we ended up with GPS. And so GPS completely changed the way we are considering location today. GPS, the first satellite was launched in '78, so that's really not that long ago. And it became fully operational in '93. In '91, a GPS receiver was still weighing 23 kilo. Imagine having a 23 kilo receiver in your pocket today. Of course, everything got miniaturized, but it's quite impressive to see how fast it evolved. So the first use was military. Afterwards, they opened it for the general public. And so I don't know how much you guys are familiar with that, but just to give a few ideas. So the way it works is that each satellite has an extremely precise clock, an atomic clock, and they're all synchronized between each other. And so continuously, each of the satellites will emit a frame saying, this is where I am, this is the time of my clock. And so that frame would be emitted, and the receiver that is on Earth would receive the different signals, different frames from the satellites, measure the time at which those frames arrive, and then using the combination of the different signals that you would hear, you would basically first reconstruct the time, because your GPS receiver doesn't have an atomic clock that is synchronized, so you need to reconstruct the time, and then you would get the time that it takes a signal to come from the satellite to the receiver, and since you know how wave propagates across the atmosphere, you would transform that into a distance, and by combining multiple distances, you would know where you are. So combining 2, 3, 4 satellites would be giving you some positions. Of course, if you make the math, you would usually need 4 satellites, but since one point is usually like on the other side of the planet or like really far into space, a few less can be enough. So that's how it works. Extremely complicated piece of technology, but that really changed the way we are using the map and navigation every day. And so in 2004, we ended up having those kind of devices where it also changed completely the way we are looking at navigation. And today, it's really amazing. We can say we are at a certain place, and then we know we need to go somewhere else, but we never do any planning. We know that we enter the car, we type the address, and it's going to get us there. And we even got before a text saying how much time it would need to get us there based on traffic. So it really changed the way we think about moving. And of course, the rise of the mobile, the digital map, the GPS, that's 3.0, the live traffic. That's what we know every day. But so what's the status of all of that when we enter a building? And actually, it's not that good today. So everybody speaks about the smart building. A building with a lot of digital services, building that would be more efficient, more productive for all the people going there, working there, living there. But if it comes to map and how you can actually move around the building, we are totally still at paper age. And of course, you go to a conference and you get a paper map. And you go to a shopping mall and you get a paper map. You know, everywhere you go, you get a paper map. And somehow, it still feels normal. It still feels like we are at the paper age of the outdoor of 20 years ago. So that's really strange to me, but that's still the situation we're in today. And still, all the blueprints, they exist. Every single company, every single building has blueprints. The architects have them. They are used for security because you're obliged to put them on the wall for the firemen to use them. And they're used for real estate, for maintenance, and so on. But it's extremely limited to only a few people in the company. And so the goal, one of my goals, is to really get those floor plans out there. Make the tools so that the floor plan is not only used by a few people in the company, but really available to everybody who needs to use it. Of course, there are privacy concerns. You don't want to get the floor plan of everybody open to the general public, so you need to make sure that everybody gets the level of details that they need depending on the role. You get maps for the visitors, for the employees, for the security people, for the maintenance guys, and that's gonna change, of course. But the goal is to get those floor plan up there, and that's one of the missions that we have for Mapwize. But on the other hand, we still do not have a global indoor positioning system. The GPS doesn't work inside because since when you're inside, you don't have any direct line of sight with the satellites. And so since what you're measuring is the time between the moment the signal leaves the satellites and when it reaches your phone, if it needs to go inside and needs to get into the building, all the time it takes inside the building, it's time that it should not have taken. And so basically, it completely messes up the measurement. And we clearly see when we are inside places, inside buildings where obviously there is, for example, only one window, that we are positioned at that window. Because that's what the signal thinks in terms of where is the last moment that signal actually deviated to the satellites. So GPS is not usable. And so that's why a lot of different companies, a lot of different engineers have thought about solutions to try to position yourself inside. And that's what we're going to look at, what are the different options, and how we can then use those to bring the digital services. And if you see mapping and positioning, they've always been quite different. And for me, it's also really important to say that it's usually done by two completely different players. You have the players, and if you read it back to the outdoor, you have the players that put the satellite in the sky and operate them, and you have the players that actually do the map that you have, that you're using every day. And it's not the same people. And the problem is that when it comes to the inside, it's exactly the same thing. There are some companies that try to do a bit both, and then they end up not really having the perfect solutions. But you really see that some companies are specialized on the positioning part, and some other on the mapping. And when we started into mapping, the last thing we wanted was to get involved with the positioning. However, in a lot of projects that we've been doing, the clients or the end user wanted to combine mapping and positioning. Makes sense, because that's what they're living every day on the road navigation. So for a few years, for 2 years, we've been building custom integration to get Mapwize maps with this specific provider, that specific provider. And at the end, it was quite complex, a lot of support, trying to get different parties to work together. And that was really not easy to handle. So last year, we decided to get into a complete open source strategy. Open source strategy, so on one side, we decided to open source a lot of things within the Mapwize ecosystem. And that was already quite complicated, handling the discussion with the investors, with the other business partners in the company. That's always quite tricky when you mention open source. But we also took the step to build the indoor location framework. So a framework that would standardize and then allow us to combine and process indoor location data. The objective was to say, we want to be able to use any kind of indoor location positioning system with any kind of other tool behind it, and those need to be working together. And so we thought, okay, all those integrations that we've been doing so far, trying to couple different providers with the mapping service that we're providing, we are going to release that in open source. And that's what I want to also talk about today during the presentation. So what does it mean to standardize indoor location? Location today is, if you look at the GPS, so coordinates, you have latitude, longitude that position you anywhere in the world. You have an altitude, you have an accuracy, that's how good your position is computed and how much noise there is inside, and you have a speed. And the speed in the GPS case, it's really separate because it's not only using a differential of the position before and the new position, but it's also using Doppler effect. So how fast you move compared to the signal. So the new chips really get a different computation over there. So there is the speed, which is part of the coordinate. And what we're missing in order to get into the inside was the floor. So in a sense, it's not that much, but we just need to add that specific component, which is which floor you're on. There was a big debate, should we use the altitude or the floor to actually use the position yourself inside. At the end of the day, for really a lot of simplicity, we took the floor because our first purpose was not to land the plane on an airfield, but to actually be able to tell you where you are. And the floor is much more understandable than an altitude, even if we can have both for specific use cases. And so when we do that, so it's not that complicated. And when you see how it works with the location on your phone today, when you want to get a position, the position your phone is at, you basically make a request to the operating system, which is iOS, Android, or even your computer, and it's going to give you an object that looks like that without the floor. So we thought we are going to make exactly the same principle and make sure that all the different providers are able to give you a certain object that looks like that and that you can use in any kind of application. In the applications, there are 3 big families of application that we can look at. The first is wayfinding. How do I get from a point A to point B? That's the most obvious situation. It's what we use on the daily basis. And that, of course, involves for the indoor multiple floors, and we can define what would be the destination. So I can say I have a specific auditorium I want to go to, or just give me the closest available meeting room, or get me one of those equipments. So, but at the end of the day, it's still getting to a specific destination. The other family is linked to asset tracking. Where are objects in my building? And objects can be of any type. You can think about medical devices in hospitals. You can think about all kind of specific devices in factories or linked to logistics. We can even consider ourselves as assets if we want to see where your friend is, or where is the surgeon that is on duty in the hospital, or where is an event staff when there are a lot of things going on, or where have the security people have been checking the building. So all of that is more in the family of asset tracking. And the last one is building analytics. How are my square feet used? And that's a very important question for a lot of building owners, because building is still one of the largest costs in every single company. So knowing how your building is used is really important. And here I'm not even thinking about retail, where they would like to see how many people enter a specific store and from what store they go to the other store and so on, because that's a whole different world. But in general, knowing how building is used is really important. So those are the 3 really large families of usage that we see. And so if we go back to indoor location, the idea is to say, whatever positioning technology that you are using, you standardize it so that any tool that you will develop in any of those 3 families, you will be able to feed exactly the same source of indoor location data. So it doesn't matter, and you will be able to also interchange them. If you say that part of the building is better for one source and part of the building for another source, you can do that. I'll come back on it in a minute. So the framework itself not only defines what an indoor location is, but it defines what a provider is. And so a provider is simply going to be a class that does everything it needs to be able to spit out the indoor location of specific devices. So you can initialize it, start it, stop it, and as soon as it detects a new location, you will get an event, did update location. In that sense, nothing fancy. It's exactly what's going on with the GPS today on most of the operating systems. But in that way, we can really standardize it. And so the goal of the framework, which is all open source, is to define those core classes, and then we are working with the community to provide as many suppliers and providers with those providers, and also potentially with sample apps. So the goal is really to make those available for using in the framework. We also have basic algorithm to illustrate principles. So if you say, I'd like to know how it works to, and I'll come back to a few examples afterwards, but put different beacons in a room, or and position myself over there, or define that I'm going to make a few steps in a direction, so I'm moving in some directions. We can also do that as part of the module. We have modules to combine multiple sources. So you can say, when I'm outside a building, I'm going to use the GPS. I'm getting inside, I'm going to switch to the Wi-Fi. I'm getting in some specific room. I'm going to get to a different technology. And we also have helpers to store, process, visualize data, making heat maps, trying to count how many people have been in certain areas, making big data analytics, like how many of us have spent most of our day listening to talk versus going to the exhibition floors and things like that. So the goal is not to replace third-party applications. The goal is really to standardize and make the development of other applications easier. But I've been speaking about indoor location system. I think I would like to say a few words about what are they? What are the different technologies that we can use today to position you inside of a building? And we see that there are basically 4 different basic principles for defining the big categories. The first one is proximity. Proximity is when you know you are close to something. And something can be anything that you can sense in your environment. So it could be a QR code that you flash. It could be NFC that you scan as well. It's the initial use of the iBeacon. So BLE, Bluetooth Blue Energy, is a standard protocol that is used to communicate between any mobile device. And at some point, Apple decided to create the iBeacon, which is nothing more than deciding that a specific frame of the Bluetooth Low Energy signal protocol would be associated with some specific capabilities. And so they said, OK, that specific frame, that will be listened continuously by the phone. And if there is an ID inside of it, and the app is been asking for a wake up when that ID was triggered, then we'll trigger the app. And so that was a really big step forward into all those proximity. And so iBeacon started as a proximity standard. Of course, proximity can come with a bit of how far you are. So if you scan a QR code, you know exactly how far you are. iBeacon, it can be scanned a few meters away. So am I really close? Am I a bit far? Am I really far? But still, that's the principle of proximity. And Google decided to afterwards launch Eddystone, which is a different standard, still based on Bluetooth Low Energy, where instead of encoding an ID, which is an ugly set of characters, you encode a URL. But at the same time, it's quite the same principle. It didn't get the same enthusiasm as iBeacon had. I'm sure Guy would have found reasons for that. But it's still an option as well in the proximity techniques. Another one that is really interesting and that I really like as well is visible light communication. So today, in the LED that is on the ceiling to provide artificial light, it is possible to add a very fast signal, a very fast oscillation in the light that the human eye is not capable of seeing, but that other sensors, and in particular the camera of your phone, is able to detect. So basically today, if you add a little component between the alimentation of the light and the light itself on the ceiling, and if you are underneath with your phone, and if you have it in your hands and the camera pointing up, you know exactly under which lamp you are. So that is giving you an opportunity to position yourself as soon as you know where the different lamps are positioned in the building. So today it's still quite experimental. So the modules are there and they are sold and they are the first deployments that are being made. But if we look at what the industry is saying, the lighting industry says that probably in 5 to 7, 8 years from now, it's going to cost them more to have 2 different line of products. And so most probably they will have the VLC module integrated in any light. So if you're going to go to the retail store and buy a LED, it will be able to give you the extra ID. And so they're bringing a lot of more stuff into it. For example, the capability of reading light data, like for how much time did the light was on so far, what's the power consumption, when is it time to change it. So all our new services around the light. What we care about here is really the fact that light can emit a special signal that can be picked up. So of course, there is also the Wi-Fi, which are the SSID that are visible, which are the APs, ultrasounds. So you need to keep the microphone on for the phone to hear it, but you can hear those things, or even image recognition. There are some tools where you actually see specific objects and you know where they've been placed, so you can use that. The good thing about proximity is that it's really easy to set up. It never gives you a really accurate position. So you know you're in a certain area, which sometimes is good enough for getting a starting point for a trip, for example, or knowing what's around you, how many meeting rooms, or far are the meeting rooms from where I am, or what are the interesting assets that are in the neighborhood. But it's never going to give you a really accurate position. The second family of tools that we can use is tree iterations. That's coming much closer to the GPS. So there we get distances between a receiver and a set of emitters, or the other way around, between one emitter and a set of receivers. So you get those distances, and from those distances we'll infer the most probable position of the device. And there we can, again, use different technologies. So Bluetooth Low Energy is an option. Wi-Fi is a different option. Ultrasound and even ultra-wideband. So ultra-wideband is specific radio communication. It says ultra-wideband because it sends extremely short signals. Basically, it sends pulses, and those pulses will be heard, and that will be used for the computation. The GPS would be typically extremely close to the ultra-wideband, so very short signal, frame of signals that you can use to synchronize that. Of course, you've already probably heard about the first three. So BLE, it's in everybody's phone today. Wi-Fi as well. Ultrasound, everybody can use it, but nobody really wants to turn on the microphone all the time. So it's usually kept for very specific applications. And you have the ultra-wideband, which is so far only available for dedicated hardware. So we use them for logistic scenarios, for drones and things like that. And I said that the goal was to get distances between where I am and where is a specific object or an emitter that I know about. Of course, I will never be able to measure a distance directly. So there are two ways that I can try to measure a distance using those kind of emissions, and they are RSSI and TOF. So receiver signal strength and time of flight. Receiver signal strength is quite easy to measure. We basically measure how much energy has been lost between the moment the signal was transmitted to the moment the signal was received. So we estimate the distance from the signal attenuation. For that, we need to know how hard what was the power at the emission of the signal. We need to measure the power when we receive it, and we know that by default the propagation is linked to the square of the distance. And that's pretty easy to understand, because if you have a certain amount of energy and it propagates, it's going to propagate on a sphere. So the more the signal evolves, and the more the energy is going to distribute on the outside of the sphere, and so that's how you get the square of the distance. So the principle is really simple. The problem is that it's really tightly linked to environment and sensitive to environment. And so signals are going to be disturbed by walls, by metal, by water, and you all know that humans are actually mainly water, so we are disturbing signals a lot. So measuring signals attenuation in a room that is empty or in a room that is full is going to be completely different. And so that's the most technology today. The most common technology today for estimating distances is RSSI. But the problem is that it's quickly not that accurate, and it's really difficult to improve accuracy because it would require a modeling of the environment that is extremely complicated to make. So the other option is time of flight. And so time of flight, we use the time it takes for a signal to propagate between the different emitter and receiver, and we divide it by the speed. And the speed is quite well known and very constant in the standard environment. And there, it's important as well to see that speed of sound is much, much lower than the speed of light. And the importance there is that if you want to have a precise measurement of the distance, you need a precise measurement of time. And so if you have a speed of only 300 meters per second, if you have an accuracy of a few milliseconds, you basically get an accuracy of a few meters or less than a meter. If you want to get the same accuracy for propagation of light and propagation of radio, you need measurements on the nanoseconds, which is still today not that obvious. And so it's usually require specific dedicated chips. We see that arriving more and more into standard materials. So the GPS is using it for 20 years. So we know how to make those chips. It's just that they didn't make it into the phones yet. There is a new protocol brought by IEEE really recently, which actually brings nanosecond time of flight measurement on Wi-Fi signals. So we're really hoping that will go through, but the distribution of the hardware that support that today is really limited. So that's a really great way of moving forward, but it's still quite costly in terms of deployment. The other one is linked to fingerprinting, and so there the idea is you measure signals at a lot of different points in your building, so you know what kind of signal there is. And when you want to position yourself, you look at the map you created and say, seeing those signals, where are the possible points where I could be? And so if you say, I've heard that signal for so many dB over there, then you will try to invert the measurements and say, this is then the place where I am. And we can use, again, the same principle, Bluetooth, Wi-Fi, but even the magnetic field, because since magnetic field is disturbed by metal and by all kind of things in the environment, which you find a lot in buildings, there are options to do that as well, that have been proven to work with more or less accuracy, but that I will also let you get your opinion on that. And so also with image recognition. The challenge here is always to keep the map up to date. Because since we are measuring, we are making a snapshot of signals that we hear in an environment, if there is anything changing in the environment, we can actually completely disturb the map of the signals, and therefore not being able to retrieve the correct position. And the last one is linked to movements. So that is not directly giving you a final position, but more a relative movement from a non-position to the position you are right now. So that's a bit what you can think of so we use it in a lot of other industries, like you have it on plane, you have it on cars, what happens when you get into a tunnel. So we basically consider that you know a starting position, you know a starting speed, you check how much time passes, and then you can use the accelerometers, the gyroscope, the pedometer of your phone or of your device to get an idea of where it goes. Of course, that's subject to cumulative error, so it means that if at some point you make an error, there is no way that you will ever be able to correct that without any external measurements. And there are also physical limitations that the accuracy of all those sensors decreases with size. And so if you look at inertial units that you put, for example, in rockets, in planes, in cars, they are more about this size, and on cruise ships or on military ships is like 10 times that. So if you miniaturize that in your phone, you will inevitably get a lot of decrease in the accuracy. Of course, next option is to fusion all those sensors and make SDKs that you can use that combine all of that. And so that is something that could be done, that is done by a lot of different providers directly into their system. Or that's something that could also be done through the open source framework that we are proposing, saying I'm hearing those kind of signals from a specific provider and some other from a different provider. What can I use in between? As for example, something we do with like trilateration on the Wi-Fi side and movement in between the measurements. And to complete a little bit the general picture about the positioning, there's still quite two other big families. One is that the position is defined device side, and the other one on the infrastructure side. So device, the idea is that the device is listening to his environment and defining himself its position. So that's exactly what you do with GPS. The satellite have no idea that you exist. It just sends signals, and the phone is actually listening for the signals and defining its position. Usually that's better for navigation, for wayfinding, because you have a much better control on when you turn it on. Since you only turn it on when you need it, you can afford to use a bit more battery. You can much better control the refresh rate. How often do you get a new position from there? So that's one of the family. The other side is more from the infrastructure side, and the infrastructure will listen to the device and be able to locate all the different devices that are there. And usually it can be better for tracking and for analytics, so for asset tracking and for analytics, because the infrastructure will not be concerned with, or will be concerned differently with energy consumption or with, and potentially as well with privacy. So that's the different families. If we look at what, for example, Cisco is doing on the Wi-Fi, the first things that they deployed was Wi-Fi positioning on the infrastructure side. Since the devices communicate with Wi-Fi, the different access points will hear the device. Of course, one access point is going to hear the device for the normal communication, but the device also emits some probe requests that will scan across the multiple channels to see what are the Wi-Fi that are available. And so those probe requests can be picked up by the different access points. From the moment that they hear a signal coming from the same device with different dissipation or attenuation of a signal, so it's RSSI, and they know where the access points are, they know kind of where the device is. So they can keep track of where the devices are. So they've been, this has been integrated in CMX, which is more on the original line of Cisco products. There's also some capabilities like that in Meraki. So that's the kind of thing that can be used as well. Yeah, so that's, you see quite a large spectrum of opportunities in positioning. So to come back to the conclusion, clearly the diversity of positioning technologies made us come to the requirement of standardization. Standardizing the way we actually use, as developers, we use those different techniques so that it makes it much easier to work with. And clearly what we felt as a pain from developers, either from ourselves or from our clients, is to say every time that we want to make a change or want to try a different provider, we need to go through a completely new set of APIs, a completely new set of requirements, and so that was really complicated and painful. So we really thought there was a need to converge to a standard for our developers. And so that's why we decided to push that as an open source framework. And so why did we actually get into the open source, and what do I see as the pros for the open source. The first thing that is really easy to work with for partners and for customers. Everybody can see the base of the code. Everybody can contribute to all the different position providers. They see how things are made. They know what to do if they want to implement their own providers. So that's really a good way to work if you have some base of code that you can share with other partners and customers. And also the customers, they really like to have open source code because it helps the developers in understanding how things work. So for pushing something, that's really good. Also, we can broaden the developments thanks to a community. So we can really try to get more people when they are involved with the framework in their daily life to actually push some more code and some projects on the framework. It clearly speeds up the adoption of the software because that's something that clear developers say today. They prefer to go for open source because they know that it's going to be easier to work with. If they have an issue, they can dig into the code, they can understand how things work, and they usually don't like to be facing a black box. Clearly, also the objective is to try to evolve toward a standard, something that everybody in the industry could use, and that would really simplify the life of everybody. And that's also why we completely put it on the site compared to Mapwize. So it has nothing to do with Mapwize. We are the main contributor to it today, but I really hope that at some point it's going to be really an industry standard. And the other thing is that it generates a lot of enthusiasm around the project. And it's also always good opportunities to present it in an event like this one. And it opens opportunities for open innovation. And for example, that happened with us recently, where we said, oh, we would like actually to have modules to process in the location and make heat maps out of them. And that's where we worked with Microsoft, and we had developers, evangelists from Microsoft spending in total 3 weeks to build some of the processors on Azure. So of course, it's a way for them to get exposure, but that ended up as an open source project, which would never have happened if all what we had done was stayed as a cloud source. Of course, the cons is that it's still quite repelling for non-tech people. So you still need to explain your investors and your other partners how come you're not just giving away free stuff, but you're actually trying to generate new value. So you really need to get deep into the idea of developer evangelism. It's an extra workload because you really want the code to be as clean, as documented as possible, because you want people to be able to contribute. And I know that sometimes when it's internal code, we can take some shortcuts. When it's open source, we really try not to do it. And it's still quite a significant effort to get that community. So it's not because you say, I'm going to try something open source, that's actually work extremely well. So that's the idea. So if you want to know more, I'm going to have a workshop today. Is it 1 or 1:30? I'm not sure anymore. But at 1:30, workshop 4, where I'm going to speak much more in depth about how you can actually use the position provided by Meraki in order to display it on the map. In the location.io, that's the website and the GitHub page. You have my email address if you want to contact me. And then if you want to try the map, you can actually scan it, and that's the map of the event. So I can quickly show you what it looked like for the 1 minute that I have left. So the idea is to, how come I'm not on the screen anymore? Yeah, very good. So the idea is to say we have the outdoor map, and so we can zoom in. That's the map of that we created for DEVNET Create, and so that's the position that is given real time from the Meraki infrastructure that is deployed in the space. So if you want to go to, for example, the workshop 4, where I'm going to give the workshop this afternoon, so you can see it's right there. And if you want to go there, you can actually get the path from the current position to your destination. So that's what I wanted to share with you. So if you have any questions, don't hesitate. I'm going to be available for the entire day and going to be at the workshop as well a bit later. Thank you very much.
All right. Thank you, Matthew. That was great. Ed just checked the schedule, and it looks like your workshop's at 1.
Yeah, I think so too. I didn't know it's 1:30 on the presentation.
Awesome. All right. Thanks again. And next coming up at 11:15, we're going to have Heidi Waterhouse, who's going to be talking about choosing your own deployment. So stick around, and we'll get her on stage shortly.